Hello everyone. Today we will be talking about ray optics and optical instruments. This topic will be covered in 4 parts. In the first part, we will be covering introduction and reflection of light by spherical mirrors. The second part, we will be covering refraction and total internal reflection. In the third part of the video, we will be covering refraction at spherical surfaces and by lenses, refraction through a prism, dispersion by a prism, some natural phenomena due to sunlight, and in part 4 we will be covering about optical instruments. Now starting with the first part, introduction. The first thing that comes into mind when we talk about ray optics is light. What actually is light? Light is basically an electromagnetic radiation belonging to the region of the spectrum with wavelength of about 400 nanometers to 750 nanometers. 1 nanometer basically is 10 to the raised power minus 9 meters. It is mainly through light and the sense of vision that we know and interpret the world around us. When light falls on our eyes, basically the eye, which is actually an optical instrument, enables us to see the things around us in the world. Now what do we know about light? We know that light travels very fast with a speed of 3 into 10 to the raised power 8 meters per second, and it travels in a straight line. But how so? It is an electromagnetic wave. So how does a wave travel in a straight line? The answer is simple. The wavelength of light is very small, that is in the range of nanometers. And if suppose we consider the light wave to be traveling from say one point to another with the distance between is centimeters, so the light wave can be considered to be traveling in a straight line joining these 2 points. The path of this wave from one point to another is called a ray of light, and a bundle of such rays constitutes a beam of light. Now this study of these ray of lights is what constitutes ray optics. The phenomena which can be explained using the ray picture of light are reflection of light, refraction of light, and dispersion of light. Using the basic laws of reflection and refraction, we shall also study the image formation by plane and spherical reflecting as well as refracting surfaces. We will then go on to describe the construction and working of some important optical instruments, including the human eye. Coming to the topic of reflection of light by spherical mirrors. Now, there are basically 2 types of spherical mirrors, namely the concave mirror and the convex mirror. Some of the key terms which you should be acquainted with before we cover this topic are the aperture of a spherical mirror. The aperture is basically the effective width of a spherical mirror from which reflection can take place. For example, in this concave mirror, this portion is the aperture of this mirror and this portion is the aperture of the convex mirror. The second term is the pole. The center of a spherical mirror is called a pole. For example, in this say, this portion is the pole, the P represents the pole of the spherical mirror. Third is the center of curvature. The center of the hollow sphere of which the spherical mirror is a part is known as the center of curvature of a spherical mirror. For example, you have a concave mirror, and if you complete this portion of the spherical mirror to form a complete circle, then the center of this circle is known as the center of curvature. The center of curvature of a concave mirror is in front of its reflecting surface, that is this side, while for a convex mirror it is behind it. This is the reflecting surface of the convex mirror, and the center of curvature lies behind this. Any ray that passes through the center of curvature strikes on the spherical mirror and reflects back through the center of curvature itself. The next term is the radius of curvature. The distance between the pole and the center of curvature is called the radius of curvature. Next is the principal axis. The straight line passing through the center of curvature and pole is known as the principal axis. For example, in this figure, this x prime x is the line passing through x prime x is the principal axis. Similarly here, this is the principal axis. Next is the normal. The normal at any point is a straight line passing through the center of curvature and that point. For example, this line here that passes through the center of curvature and that point is called the normal. Next very important term is the focus. The point on the principal axis where all the rays coming from infinity after reflection either meet or appear is called the focus. We will be covering the focus of the spherical mirror in detail in the coming 4 slides. The focal length is basically the distance between the pole and the focus. For a spherical mirror, the focal length is basically half of the radius of curvature. That means this radius of curvature, so for example, the focal point or the focus of a concave mirror will lie somewhere here in the middle of this segment, and similarly focal plane, an imaginary plane passing through the focus and at right angles to the principal axis is called the focal plane of a mirror. We will be covering focus of a concave and convex mirror in detail in the coming few slides. Coming to the laws of reflection, there are basically 2 laws of reflection. For example, you have a plane mirror. If light is incident on it and gets reflected by this mirror, then the first law of reflection states that the incident ray, the reflected ray and the normal all lie in the same plane. The second law of reflection states that the angle of incidence, which is the angle between the normal to the plane to the mirror and the incident ray, is the angle of incidence is equal to the angle of reflection, which is basically the angle between the normal and the reflected ray. Some important sign convention which is required to study ray optics is, first of all, the principal axis of the mirror is taken along the x-axis. So this axis is the x-axis, positive direction of x-axis. Here we have basically a concave mirror, and this axis in positive direction is called the principal axis. The object is taken on the left hand side of the mirror that is incident on the mirror from the left hand side. This is the left side of the mirror and this is the right side of the mirror. So object is always taken on the left side of the mirror. All the distances parallel to the principal axis of the spherical mirror are measured from the pole of the mirror. For example, if I have an object here, the distance from the mirror of this object will always be measured from the pole. This point is basically the pole of the mirror. This distance is basically the distance of this object from this mirror. The distances measured in the direction of the incident light are taken as positive and opposite is taken as negative. So for example, here we have an object which is emitting light in this manner. So this is the direction of the incident light. So all the directions, all the distances in this direction will be positive and all the distances measured in this direction will be negative. The height measured upward and perpendicular to the principal axis of the mirror are taken as positive. That means if it is in upward direction, the height will be positive, and if it is in downward direction and perpendicular to the principal axis, it will be taken as negative. These are some of the important sign conventions one must remember while dealing with reflection through ray optics. Now, as discussed earlier, the focal length of spherical mirrors. As mentioned earlier, when a ray of light coming from infinity gets reflected from a concave mirror or a convex mirror, it always converges at its focal point. In the picture shown here, the A part is basically the concave mirror where all the light coming from infinity basically converges at a point called F. Here this point F is the focal point, this P is the pole and C is the center of curvature, and it lies somewhere in the between. So this F is the focal point and is on the left hand side, basically on the reflecting side of the concave mirror. Coming to a convex mirror, as said earlier, all the light coming from infinity shown in the form of parallel lines gets reflected from a convex mirror and converges at the focal point. Now the difference between these two focal points is that the focal point of a concave mirror lies in front of it, while the focal point of a convex mirror lies behind it, behind the reflecting surface. The C portion of this picture basically shows that if the parallel axial beam of light were incident making some angle with the principal axis, the reflected rays would converge from a point in a plane through F normal to the principal axis. This is called the focal plane of the mirror, which states that if, for example, the light is directed on this mirror at a particular angle and it is not parallel to the mirror, it is at a certain angle, then it will get reflected and it will appear to converge in the focal plane that is shown with the help of a parallelogram in this picture, will appear to converge in this focal plane of the mirror. These are some of the important points which one must remember while dealing with reflection through spherical surfaces. Now, what is the relation between the focal length and the radius of curvature? For example, let's say with the center of curvature of a mirror, consider a ray parallel to the principal axis striking the mirror at M. Let this be the incident ray. Then CM will be the perpendicular to the mirror at M. Let theta be an angle of incidence which is this, and MD be the perpendicular from M on the principal axis, this. Then angle MCP in this picture, which is this one, MCP, is also equals to theta, and angle MFP will come out to be 2 theta. Now if I get tan theta, that means MD by CD, that it's tan theta, that is perpendicular by base, and tan 2 theta will come out to be MD by FD. For small theta, which is true for paraxial rays, tan theta can be considered as theta, and tan 2 theta can be considered as 2 theta. So equation 1 can be written as FD is equals to CD by 2. That means this distance is twice the distance between these 2 points. Therefore, if we call this distance FD as F, that is the focal length of the mirror, and this distance CD as the radius of curvature, that is R, then the focal length comes out to be half of the radius of curvature, and this seems to be true for both concave as well as convex mirror.